Kansa nga chaw a join na mitang kha link pakhat khan la join mo ni o chunchu ananta khana join mal duga clock culture to se ga start lo kan link down shit. All right. I think majority of you have joined. So I think we can start. My screen sharing is on. All right. So you can enter your attendance in the chat box as usual. Today I'm going to start a few introductory lecture on basic concepts of instrumentation, and then we can move on to cathode ray oscilloscope. Then later, after finishing cathode ray oscilloscope, we can get back to dynamic and static errors and uncertainty in measurement and all. So I think this basics of instrumentation is quite simple to every one of you. An instrument, as we know, it is a device for determining the value or magnitude of a quantity. But in designing a measurement instrument, uh, some parameters which are needed to be considered are uh, as given here. See, whenever you are performing a measurement, your measuring device or your instrument or your sensor, whichever is going to uh, be in touch with your measuring object, the object you are measuring, that should not alter the circuit conditions, or that should not alter the physical quantity, that should not alter the object. Like, for example, suppose you are trying to measure the diameter of this, let's say, a sphere. So when measuring the diameter of a sphere, if you are applying, if in trying to measure the diameter of this sphere, suppose the force you exerted on the sphere using this measuring instrument is too large, this could deform your sphere. This could deform your sphere, or this could alter the dimension or the shape of the object you are measuring. So that condition has to be, I mean, that has to be considered. uh, Whatever instrument you're using for measurement, it should not alter the object you're measuring. So uh, in geology and other things, if you're going to measure some quantities, the measuring apparatus you are going to use is usually relying on what is called pressure sensor, called piezoelectric crystals and all. So when you are applying such detector on the object you're measuring, that detector should not alter the circuit condition of the object. And also the power consumed by it should be very, very small. And here we have defined what is called the true value. We will get back to this uncertainty in measurement and dynamic and static errors in measurement. See, suppose you are trying to measure the length of an object. So when you are measuring the length of an object, what you need is a measuring scale. So when you use a measuring scale that can measure the length of such an object with an accuracy of, let's say, certain three decimal points. So if you perform such kind of measurement, uh, uh, a single measurement might not give you the actual value, the true value. So only after you perform a large quantity of measurement and take an average of such measurement, then whatever you measured value can be considered as a true value. So an error, by simple definition, it is simply the difference between the measured value and the true value. So whenever we are referring to a true value, uh, a single apparatus which can have certain defects or certain uh, parallax errors or any kind of error, it might not exactly give you a true value. A true value of a certain quantity can be measured, can be obtained only after having a large quantity or infinite number of measurement. Now, this is a certain measurement system, block diagram of a measurement system. So here, what we are going to need is a sensing element. Sensing element, it can be what is called strain gauge here, strain gauge or piezoelectric crystals. So this sensing element uh, is also considered, also known as a detector. So this will sense a certain quantity, a certain measurement, and that will be processed through what is called signal conditioning and signal processing elements and all. And then after that, we present to what is called the display devices and all. So nowadays, most of our visual display devices are relying on a digital system. So we in most cases we need what is called analog to digital converter. And you see that uh, if you go down to that geology center there near our college ground also, there also we have a sensor for earthquake and all. So the display device is now a computer device. So to display certain data in a computer, you are going to need this analog to digital converter. So converting from analog signal to digital signal, analog signal means a voltage signal, okay, alternating current signal. So when you have an alternating current signal, however small it may be, this alternating current signal slowly continue, uh, like AC signal, it's called an analog signal. So, but a computer device and all, the computer process data to what is called digital system. So always nowadays we are using this analog to digital converter, and you can refine such digital data, uh, filter out certain unwanted errors and all, so unwanted noise and all. So this process that is consisting of analog to digital conversion and this filtering or digital signal processing is called, the whole system is called signal processing system. And your visual display system, as I say, it could be a computer device or uh, in analog system. In analog system, we use what is called cathode ray oscilloscope and all. But as I said, mostly this CRO and all are no longer used. You are equipped with digital computers and all for your display devices. So Suppose you want to measure uh, a certain data, geological data, whatever, and there will be a certain load cell, and that will be connected with what is called your piezoelectric crystals or your strain gauge. So when you are applying a pressure on it, that pressure will be converted into electric signal by the strain gauge. Pressure will be converted into electric signal by a strain gauge. So actually, when you are applying pressure and all on piezoelectric crystals, the resistance of the piezoelectric crystals will change. So with the change in resistance of that such kind of piezoelectric crystals, we can convert that pressure applied into electrical signal. So that electrical signal can be amplified from few millivolts to a certain value, a certain magnitude of voltage, and that can be again processed. This voltage can be directly supplied to your CRO, cathode ray oscilloscope, uh, to display using your analog device. But you can even convert to this digital system and display it using your digital computers. That is one way of doing it. And yeah, this is something which is not so relevant. So before today, like I think we should discuss about this cathode ray oscilloscope, and then maybe we can come back to errors in measurement and all. So your cathode ray oscilloscope, which you are going to use it in your lab also, it consists of what is called cathode ray tube and vertical amplifier and horizontal amplifier. So cathode ray tube is equipped with what is called evacuated glass envelope, something like this. And within this evacuated glass envelope, you have what is called an electron gun assembly. An electron gun assembly consists of this cathode with the control grid, which is connected to negative potential cathode. With this is a there is a what is called a heating filament. So electron gun assembly consists of this heating filament and the cathode. So this cathode is indirectly heated in the sense that you are not supplying the heating current or large quantity of current to the cathode. You are supplying large amount of current to this heating filament, and the heated filament heats the cathodes. So when the cathodes is heated indirectly via this heating filament, this cathode will emit free electrons via what is called thermionic emission. So there's an electron emission process from a metal surface uh, via this photoelectric emission as well as uh, thermionic emission. So in this photo emission process, you are signing the cathode surface with photons, high energy photons. And if the energy carried by such photon is greater than the work function of the cathode, then uh, that photon, when it strikes the cathode surface, it gives large quantity of energy to cathode surface, and uh, then that results in emission of electrons. So that is called photo emission process. So that is something we already know in the Einstein's photoelectric effect. And thermionic emission process is also something similar to that. In this thermionic emission process, instead of giving energy to the cathode surface via high energy photons, you are giving energy to the cathode surface through heating. So when you heat this cathode using this heating filament, if you sufficiently heat it to a high temperature, the energy supplied to this cathode, it would then be greater than what is called your work function. The work function, as we know it, it is the minimum amount of energy required to release electrons from a metal surface, right? So that will result in emission of free electrons from the cathode surface. So if you sufficiently give large quantity of heat energy, then if the heat energy supplied is much greater than the work function of the cathode, then some amount of like uh, heat energy supplied will be used up to overcome the work function, and the excess amount of energy will be converted into kinetic energy. Excess energy will be converted into kinetic energy of the emitted electrons, kinetic energy of emitted electrons. So you can see that when you heat this cathode, it will generate large quantity of free electrons. Not only that, those free electrons will have large amount of kinetic energy. They will tend to randomly go in various directions with this random kinetic energy uh, uh, with a randomness in direction. Okay, so that those uh, those free electrons which are released randomly with a high kinetic energy in various directions, they will be controlled via this control grid. So the control grid actually say the control grid actually is mm, a certain kind of cylindrical cap that is at a negative potential. Okay, so this is a kind of cylindrical system which is connected to negative potential. So when you release large amount of free electrons in with a random direction with high kinetic energies, and this negative potential supplied to this cylinder here, this cylindrical metal is connected with negative potential. This will repel this will repel these scattered electrons, and this control grid will kind of release the electrons in this direction via this pinhole in that cylinder. Okay, so this is connected to negative potential, means this will apply a repulsive force to these scattered electrons. So for those electrons released from the cathode, instead of getting scattered in various directions, they will be kind of uh, deflected, and via this negative potential supplied to this control grid, they will be deflected, and those electrons will be released through this pinhole in this cylindrical control grid. So this assembly is called your electron gun assembly. And as a result of this electron gun assembly, we can say that we have a high kinetic energy electrons traveling like this, high kinetic energy electrons traveling in this direction. Okay, and once it is released from this, pinhole of this control grid, cylindrical control grid, it will be acted upon through this accelerating anode. So this is also a kind of metal cylinder, and this focusing anode is also a kind of metal cylinder. Both this focusing anode and this accelerating anode, they you see that these are anodes, means they are connected to positive potential. So via this positive potential or the accelerating voltage applied here, these electrons will be accelerated across this uh, evacuated glass envelope. They will be accelerated across this evacuated glass envelope and pass through this cylindrical tube. Okay, so they will kind of give attractive force to those ejected electrons from this control grid, and they will be accelerated under the action of this uh, positive potential applied to this accelerating anode, and uh, this focusing anode, which is also connected to positive potential. By adjusting the focusing anode, we can control the 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 spread of this release cathode rays or the electrons from this electron gun. Now, the magnitude of the accelerating field is given by something like this. So here VA is simply the accelerating anode voltage. So you are connecting a certain anode voltage here to this accelerating anode. And if VA is your accelerating anode voltage, and if D is the distance between the cathode and the anode, accelerating anode, then E will be the electric field applied on the electrons or the charge that are released from this electron gun assembly. So the force acting on such charge will be electric field multiplied with the charge. Okay, E into Q will be the force. So you know that from Newton's equation of motion, force is in mass into acceleration. So acceleration of the electrons released from the electron gun assembly will be given by this. Acceleration will be EQ upon M. Okay, E is the electric field intensity due to the accelerating anode. Q is the electronic charge, the charge carried by those electrons released from the uh, electron gun assembly. M is the mass of an electron, and A is the acceleration produced due to the accelerating field, the accelerating anode. So using the expression for electric field over here, VA upon D, you can say that this is the acceleration produced by the accelerating anode. And during the period of this acceleration from this control grid to this accelerating anode, this is the distance D here. So during this period, the electrons will gain kinetic energy because it is accelerated, means it will gain kinetic energy along the direction. So the kinetic energy half mv square, will be the potential applied into charge. Okay, kinetic energy is potential applied into charge. So the velocity gained by an electron will be given by this kinetic energy. I hope you are familiar with this thing. Potential into charge will be your energy. Potential voltage into charge will be your energy, electron volt. Okay, electron volt, this will have an unit of electron volt. This is your kinetic energy, the kinetic energy gained by cathode rays or the electrons via this accelerating anode. So the velocity gain during the process of acceleration will be given by this. Now so after the electrons leave the electron gun assembly at a speed given by this expression as given above, it again passed through a region controlled by the deflection plates. Okay, the deflection plates. So there are two types of deflection plates here in this cathode ray tube. In this cathode ray tube, as shown here, there are two types of deflection plates. One is called vertical deflection plates. Another one is called horizontal deflection plates. So these vertical deflection plates and horizontal deflection plates, they are actually a part of this cathode ray tube. Vertical deflection plates and horizontal deflection plates are a part of cathode ray tube. Okay. Out here, you see that oscilloscope consists of cathode ray tube, vertical amplifier, horizontal amplifier, sweep generator, trigger circuit, and associated power supplies. So this vertical amplifier, say here we have said that using this strain gauge, we are converting a certain amount of load on our sensor into an electrical signal, small electrical signal. So such small electrical signal will be amplified, and this electrical signal before it is supplied to these vertical deflection plates and the horizontal deflection plates, it passes through what is called vertical amplifier and horizontal amplifier. So after it passes through vertical amplifier and horizontal amplifier, the amplified signal from your detector will be supplied to your vertical deflection plates and horizontal deflection plates. So let me repeat, whatever signal we detect using our detector, that could be your transducer or your strain gauge or your piezoelectric crystals, which converts your applied pressure into an electrical signal. So such small electrical signal will be amplified through this vertical amplifier and horizontal amplifier, and uh, such information from the detector will be supplied to the vertical deflection plates and the horizontal deflection plates. So the vertical deflection plates and the horizontal deflection plates, they will carry the information obtained from your detector. Okay. Vertical deflection plates and horizontal deflection plates, they carry information obtained from the detectors. So this cathode ray tube assembly, this CRT, although it generates this cathode rays or the electrons, and then it accelerates those electrons. So the accelerated electrons are passing through these cylindrical tubes, this control grid, focusing anode and the accelerating anode, and they are accelerated via the potential supplied to this anode VA. So these accelerated electrons, they are then passed through the deflection plates. The deflection plates will deflect those cathode rays or the accelerated electrons, depending on the information received from the detector. They will either deflect to a very large value or deflect to a small value, depending on the information received from your detectors. Okay, the detectors, whatever signal coming from the detectors, they are supplied to vertical deflection plates and horizontal deflection plates via amplifiers, vertical amplifier and horizontal amplifiers. Okay, now let's say the length of the deflection plates, let us consider only the vertical deflection plates for now. Let's say the length of the vertical deflection plate is L and the separation between the plate is D. Okay. Then if Vd is the magnitude of the deflecting voltage, Vd is the magnitude of the deflecting voltage, that is the signal which is amplified and connected to the deflection plates. Vd, let's say it is the magnitude of the deflecting voltage, magnitude of deflecting voltage. Then the intensity of electric field between the deflection plates. Between these deflection plates, the intensity of the electric field, which is given by ED, will be potential upon separation of the two plates. So potential upon distance between the two plates gives you the intensity of electric field. Okay, I hope you are familiar with this electric field and potential relation. Electric field is simply potential difference upon the distance between the 2 points where you measure the potential difference. So that gives you the electric field between the two plates. So ED will be equal to VD upon D. And this field, this deflection field, uh, it will exert a deflection force. It will exert a deflection force to this incoming charge. So you see that there is accelerated charge, that is Q here, and once it passes through these deflection plates, they will undergo deflection under the action of this your electric field. No, that's your electric field. And so So the force exerted on such incoming charge, it will be given by electric field into charge. Okay, electric field into charge. So this is called what is called the deflecting force. The deflecting force exerted on the accelerated electrons by these deflection plates. So here, if you substitute ED as VD upon D, this is what you're going to get. So let's say, according to Newton's law of force is mass into acceleration. So let's say AY is the acceleration along the y-axis. Earlier here, we talked about acceleration of the charge. This acceleration is along the horizontal here, along the horizontal here. So as you pass through this accelerating a node, this accelerating a node accelerates the charge along this direction. But the acceleration here, AY denoted here, is actually the acceleration in the transverse direction. Acceleration on the charge in a transverse direction under the action of these deflection plates. Now, therefore, from this relation, you will find that your AY will be equal to VdQ upon MD. This is acceleration along the y-axis. Now, I think it can be shown here in this figure. Here, L is the length of the deflection plates, and D is the separation between the two deflection plates. And here, VD is your deflection potential, and the electric field, the transverse electric field, the deflection electric field is VED is equal to VD upon D. All right, and AY is the acceleration along the y-axis. Now, if you remember this equation of motion, I think this is something you have already studied in your elementary school from class 9 or class 10. This is an equation. Uh, Here, S is the distance covered, U is the initial velocity, T is time, A is acceleration. Okay, so here, if you look at this, as the charge enters this deflection plate, as the charge enters this deflection plate, the initial velocity along the vertical direction, u along the y-axis, initial velocity u along the y-axis, or velocity along the vertical direction, u is 0 here, right? U is 0 here, unless it is acted upon by this deflection plate. U is 0. Initial velocity along the vertical direction is 0. So if you look at this equation, initial velocity is 0 into t plus half at square. A is your acceleration along the y-axis, at square. Okay, so as it passes through these deflection plates, the vertical distance it covered here, that is h here. Okay, the vertical distance it covered, h, will be equal to half of ay t square. The vertical distance it covered under the action of these deflection plates, as you see in this figure, this is denoted as h. So h will be ay into t square, half of ay t square. So from this relation, you put the value of ay here. Ay is vdq upon md. So by putting that, vdq upon md, half ay into t square. Yeah, t is the time required for electrons to pass through the deflection plates. So the time spent by an electron to pass through this deflection plate is denoted as t. So and we already know that the velocity, horizontal velocity, or the velocity along the x-axis there is v, which is given by, say, the velocity gained through this accelerating a node. The velocity gained through this accelerating a node is v. So due to this velocity, it will travel in this direction. So v is the velocity in this direction, and if t is the time taken here, L is the length of these deflection plates. The time taken to pass through these deflection plates will be given by velocity upon length, v upon L. I hope you understand from this calculation here. V is the velocity gained due to the accelerating a node, and that is along this direction. You can see this in the figure. and L is the length of the deflection plate. So T is the time required to pass through such deflection plate. So the time required to pass through the deflection plate will be given by velocity upon length. All right, and velocity upon length, T is equal to V upon L. Sorry, and I reverse the sign, so L upon V. Now you can put T value here. T will be L square upon V. So you can check from the dimension. Actually, V is a distance upon time. So this was a mistake. Okay, V you can this has to be L upon V. You can see from the dimension also. So you just put the value of T here. There you will find the height, the distance it covered in the vertical direction due to these deflection plates. So it deflects by an amount h value. It deflects by this h value. This much quantity is it deflects by this much height as it passes through this deflection plate because of this deflection potential Vd. So that is given by this here. Okay, now here we can see that theta here, theta is defined like this. So in reality, if you have a deflection plates and if you have an incoming charge here, this incoming charge, they will be slowly deflected continuously, slowly and but continuously deflected as it passes through this deflection plate. But uh, the onset of deflection will start immediately after it enters this deflection plate. But out here, probably the deflection onset at this deflection onset, the amount of deflection is very, very small. So for an approximation, we can assume that this is the direction of the beam. For an approximation, we can assume that for simplicity in our calculation, we can assume that this is the direction of the beam. So let's say this L is the length, and let's say this is your L upon 2. So for simplicity in our calculation, we can we can approximate the direction of these electron beams to be something like this. Traveling in this direction from half of the length of the deflection tube. Okay, even though there is a small onset of deflection here and continuously deflecting in this direction. So for simplicity in calculation, we let us assume that the direction of the beam is the direction of the electron beam is something like this. So let's say this is your theta and h is the height here. H is the height here, L upon 2 is the length here. So your tan theta will be opposite H upon base, H upon L upon 2. Okay, your tan theta will be H upon L upon 2. So for small angular approximation, if you remember, there's this thing called Taylor series expansion of tan theta. This is equal to theta minus theta square upon 2 factorial plus theta cube upon 3 factorial, something like this. So if the angle of deflection is here, usually the angle of deflection is very, very small. Let's say 0.08 degree and all. 0.08 degree and all. So your theta square will be 0.16, but there will be 0.0016 degree for theta square. Then theta cube will be even smaller than this. So for small theta, for small angle of deflection, your tan theta can be approximated to be equal to theta, because the higher order terms, theta square and theta cube terms, can be neglected because they are getting very, very small, right? So tan theta can be approximated as theta. So your theta can be written as h upon L upon 2. H upon L upon 2. So here, for simplicity, I said that we can approximate the direction of the electron beam something like this, as if it is traveling in this direction from half of the length of the deflection tube, H upon L upon 2. And from this same figure here, we can also write sine theta Sine theta will be opposite y upon hypotenuse is r, y upon r.